Hi, my name is Zirui. In this video, I'll be presenting our work Resource-Aware Distributed Submodular Maximization, a paradigm for multi-robot decision-making. Let's get started with 3 multi-robot decision-making problems. In the task of collaborative monitoring, a group of drones seek to coordinate their actions to maximize the area covered by the whole team. However, a complication arises that the onboard resources for communication, and memory are always limited, so that not every drone can communicate with everybody else. This complication motivates the problem that how the drones can coordinate with only a few others and at the same time use onboard resources as little as possible. For collaborative mapping, a team of mobile robots coordinate their actions to maximize the total area mapped by their cameras. Similarly, there's a complication of onboard resource limitations. Therefore, the robots also need to coordinate with only a few others in a resource-aware manner. And for collaborative target tracking, the goal becomes capturing the most ground targets by the drone's cameras. And still, they have limited onboard resources. Therefore, the problem of resource-aware coordination is motivated once again. All the problems above can be formulated as the following distributed maximization problem. First, there are a finite set of agents n. Next, the agents will perform distributed communication. That is, each agent I can receive information from its in-neighbors ni- only. Then, using the received information, each agent chooses an action from its finite available action set vi. For example, this vi can be a bunch of motion primitives over the next 10 seconds. Finally, the task utility is captured by a set function f, whose argument is all the agent's actions. Given these inputs, the agents want to perform an algorithm to collaboratively maximize the function f by each independently selecting an action. In particular, the aforementioned task utilities can be captured by monotone non-decreasing submodular functions. Here, non-decreasing means the more robots are deployed, the larger the utility will be. Submodular means the more robots are already deployed, the less is the marginal gain given by deploying one more robot. Also, all the applications above can also be modeled as second-order submodular, which means when more robots are already there, the marginal gain of deploying one more robot will be less. This problem of distributed monotone submodular maximization has been long investigated in the past few decades by many researchers, just to name a few here. But this problem with merely distributed communication doesn't solve the complication of limited onboard resources. Why? Let's look at this classical paradigm for the problem, which is sequential action selection. In this paradigm, the agents are first ordered in a sequence. Then, each agent will receive the information of all the previous agents for making its own decision. Therefore, due to the distributed nature of the communication network, it requires a lot of communication rounds to deliver the information, and the communication messages will have an increasing size. For example, here the blue robot sends only its own information to the orange one at the first round, so the size of message is just 1. Then, at the second round, the orange robot's information is also transmitted together with the blue robot's information, so the message will be of size 2 now. At the third round, the information of the blue, orange, and green robots is all transmitted, so the size of message increases again, and so on and so forth as the information is passed forward. In short, the current popular sequential paradigm will lead to increased communication latency as well as increased memory usage for inter-robot messages, and this actually violates our resource-aware requirement for multi-robot coordination. To this end, we propose to let each agent require information not only from in-neighbors only, but also about in-neighbors only. That means each agent only transmits its own information instead of also transmitting previous agent's information as a relay node. Therefore, the memory requirement will not grow, multiple agents can choose in parallel, and the communication latency and computation requirements will also be reduced. In this way, we achieve the resource awareness. The formal definition of resource-aware distributed submodular maximization is as follows. With the distributed communication, each agent I is given an in-neighborhood ni-, a finite action set vi, and the monotone submodular and second-order submodular function f that captures the task utility. And based on information from and about enablers only, they want to each select an action to collaboratively maximize the function f. This problem formulation is different from the merely distributed submodular maximization above, as here each agent requires information not only from enablers only, but also about enablers only. Solving this problem is difficult, since even when the communication topology is centralized, that is, even when all the agents have access to all the other agents' information, this problem is still hard, and it's been proven that the best approximation ratio of a polynomial time algorithm is 1 minus 1 over e. So what a good resource-aware approximation algorithm should be like? We think 4 dimensions should be addressed: computational efforts, communication rounds, memory usage of messages, and approximation ratio. For computational complexity, we think being linear in number of available actions is the best we can get, because an agent at least has to scan all of its available actions to find the locally best one. For communication rounds, we say sublinear in the number of agents in general due to parallelization is desired, but being linear is also fine if in the worst case where parallelization is impossible. For memory usage, we want the size of messages to be constant instead of increasing, as shown in the example above. Finally, we hope the approximation ratio to be as close to 1 minus 1 over e as possible, which has been proved to be the best achievable bound for monotone submodular maximization. With all these characteristics, the ideal algorithm should enjoy low computation, low communication, constant size of inner robot messages, and the best possible bound close to 1 minus 1 over e. The state-of-the-art stands as follows. We can see that, while these works approach the ideal algorithm in certain aspects, they all also suffer from some other aspects. For example, Robe et al. Achieves an approximation ratio close to 1 minus 1 over e, but requires over 20 minutes for monitoring tasks with just 10 robots. And Konda et al. Achieves optimal computation and near-optimal communication requirements, but suffers in terms of memory usage of messages, because this method instructs each agent to sequentially acquire all previous agents' information. In this work, we provide an algorithm that has near-minimal computation, communication, and memory usage for an arbitrarily given communication topology. This communication topology can be from the whole spectrum from full centralization to full decentralization. Look at this figure. Our algorithm is represented by a line. And the upper right end is the fully centralized case, which recovers the 1/2 near optimal approximation performance and requires near minimal resources. And the fully decentralized case is on the other end, where the suboptimality bound can still be non-zero despite full decentralization, and all the resource requirements will just be minimal since there's no coordination. In all, our algorithm captures the suboptimality cost of decentralization via decentralized quantities as a function of the in-neighborhood. It also achieves near-minimal resource requirements. Moreover, it holds with any communication topology from full centralization to full decentralization. Then, let's see how the algorithm works. Our algorithm, resource-aware distributed greedy, or ROG, enables multiple agents to select actions in parallel. First, all the agents simultaneously find their candidate actions that give the largest marginal gains. For example, here, this action 1 will be the candidate. Then, each agent will compare its candidate with the candidates of its in-neighbors only. If its own candidate is better, then it chooses this candidate as the next action. Otherwise, it doesn't select and just continues on the next iteration. In this way, multiple agents may select actions in the same iteration in parallel, and the algorithm will terminate once all agents have selected actions. Now, let's focus on the approximation performance. The key question here is actually how to quantify the suboptimality cost due to decentralization, or say due to ignoring the non-neighbors. By non-neighbors, we mean all the other agents that are not in neighbors. To this end, we propose a novel notion, centralization of information among non-neighbors, or coin, to quantify the suboptimality cost due to decentralization. Coin is defined as the mutual information between my action and my non-neighbor's possible actions. It's a function of the in-neighborhood, or equivalently, non-neighborhood. In this figure, for the monitoring task, I'm far enough from my non-neighbors. Then, my action will be decoupled from theirs. So intuitively, ignoring them will not affect me at all. And as this figure shows, now coin is 0, which coincides my intuition that ignoring non-neighbors is totally fine. But, when I'm quite close to my non-neighbors, intuitively ignoring them will affect me. As this figure shows, now the gray area will be coin, which means if I ignore my non-neighbors, I may suffer some cost, and the amount of this cost will be no more than this gray area. After capturing the cost of decentralization using coin, we provide the suboptimality bound of our algorithm. The result of the approximation algorithm will be greater than or equal to a half of the optimal function value minus the sum of coin. Therefore, this bound is a function of all agents in neighborhoods. The larger the in-neighborhoods are, or say the more centralized the communication topology is, the higher the bound will be. The scenario with fully centralized communication is located, as we said, at the upper right end of the line representing the algorithm. In this case, our algorithm recovers the classical one-half near-optimal centralized performance, because now there's no non-neighbors for any agents, and coin for everybody will just be 0. The fully centralized case has an approximation ratio very close to 1 minus 1 over e, but the computation and communication requirements are also relatively more than in not fully centralized cases. The case of fully decentralized communication is located at the lower left end of this line, where the bound will take its worst value because for each agent, all others are non-neighbors. Now the bound becomes 1 minus curvature over 2 minus curvature, where curvature is a metric commonly used in literature that evaluates how linear or say how modular a set function is. In many scenarios where curvature is less than 1, this bound is non-zero. In some worst scenarios where curvature equals 1, this bound will be 0, but this is also expected since no coordination happens anyways. Finally, let's consider the simulation of collaborative monitoring with 10 robots in a 50 by 50 grid map. All the robots have the same monitoring range 10 grids, the same action set of forward, backward, left, right by 1 grid, and the same communication range which is however unfixed yet. That means the robots in neighborhoods can be adjusted by changing the communication range. We are interested in the evolutions of the team's coverage utility as well as the resources usage as communication range increases from 0 to 50. The simulation results show that as the communication range increases, or equivalently, as communication becomes more centralized, more resources for computation, communication, and memory will be used. At the same time, the coverage performance will be better. This is expected since as communication becomes more centralized, the robots will have fewer non-neighbors, and coin will just approach 0. Moreover, after plotting this graph, we know that when communication range is 6, the trade-off of centralization versus decentralization is balanced. That is, the robots can achieve a pretty high coverage performance while consuming very few onboard resources. In all, we have proposed an algorithm for distributed monotone submodular maximization that captures the suboptimality cost of decentralization as a function of the in-neighborhood, which is a decentralized quantity. Compared to the state-of-the-art, it requires near minimal computation, communication, and memory usage. Moreover, it holds with any communication topology, from full centralization to full decentralization. In the future, we would like to enable an active design of communication topology to enable fluid networks subject to the resource constraints of each robot. Also, we will enable its application to tasks that cannot be captured by submodular functions.